So hello everybody. I would like to welcome you to today's webinar, What's New in Virtual Dynamics 2019.0. First, I'd like to introduce myself as the moderator of this webinar. My name is Christoph Donker. I'm the marketing manager of VV Software and Testing Solutions. That will give you short information about this webinar. The webinar will be presented by Mr. Mustafa Douya and Swapnil Shah from the Virtual Dynamics team. The duration will be around about 45 minutes, including a live presentation of Virtual Dynamics. And if you have questions during the webinar, please feel free to send them with help of the small panel on your screen. And if you have enough time left at the end of the webinar, we will give you the answers. Virtual Dynamics is an advanced simulation software for dynamics analysis of powertrain, driveline, and their components. The highlights of the new release 2019.0 are multi-thread computing, clutch element, and chain drive enhancements. So let's start to learn more about these interesting features, and I'd like to hand over to Mustafa Douya. So enjoy your webinar.
A brief information about what was new in the latest version that we released last month on 15th of April. So Virtual Dynamics 2019.0 supports Adams 2019.0. The functional changes include multi-threading computing, clutch element, and chain drive enhancements, but they are not limited to that. For the full scope of enhancements and as well as some fixes, please refer to the release notes that you can find it which comes with the installation. So the first is Virtual Dynamics goes multi-thread. We are very excited with this. It's a great enhancement to improve your efficiency and developing the products that you are working on faster, which means lower cost products on the market. It provides significant simulation time gain across different applications that we will go over today. Even with additional thread, improves the simulation time about 30%. You can achieve a factor of 2 even more simulation time gain running on 4 threads. So these improvements are available even on standard laptop computers, and we expect better performance on real HPC clusters. So I'll go over a couple of case studies that we did with multi-thread computational capability. So this is an EHD elastohydrodynamic bearing case study based on a heavy-duty diesel inline 6-cylinder engine. This is very high fidelity model which is composed of flexible engine block, flexible crankshaft, flexible con rods, and 7 main bearings are elastohydrodynamic bearings. We run this simulation on full load at 2000 RPM for 2 cycles on a laptop computer that you can see the details of the computer on the bottom of this slide. So if it is run on 8 threads, when compared to a single thread, it is 3.3 times faster. And if you have available 8 threads on the computer, afterwards, after this study, we also run the same model on a laptop computer again, which has 12 cores, 12 threads, in other words, and it was even faster, even though we just used the 8 of 12, it was 4 times faster when compared to single thread. There are 3 more case studies that we did. The other one is inline 6-cylinder engine again. This is a crank train study, which is composed of flexible engine block, flexible crankshaft, flexible con rods, and this time hydrodynamic bearings. Then the next is a timing mechanism, silent chain with external geometry, and hydraulic lash adjuster along with the sprockets, of course. And the other study is about a gear train. Actually, it is a transmission that is coupled to inline four-cylinder engine. The engine is rigid for this case. We have a clutch disc, flexible gear and clutch housing, and flexible gear shafts along with spline gear force. And here are the results. If we compare the crank train model that we run on idle and full load, when compared to a single thread, 8 threads is about 2 times faster. The timing mechanism is about 2.5 faster when compared to a single thread, and the transmission model along with the engine, it is about 2 times faster when it is run on 8 threads. And it was Intel i7 CPU, which has 8 threads and 32 gigabytes of memory. So again, I would like to mention once again the gain of simulation time even better on real HPC kind of clusters. So the next new feature is a brand new clutch element that we introduced with this release. You can see the screenshots of the dialog boxes on which you define the typical parameters of the clutch. So we support both single and dual clutch topologies. For addressing stick-slip behavior, we are using Lugri friction model as well as we capture Strebeck effect and the viscous damping. Optionally, we can also have clutch plate in the clutch plates spring damper to address individual torsional stiffness and the damping per clutch. And it is crucial for starting effects, to study the starting effects. This is just one single use case, that V6 engine running on a test bench, and test bench is driving the plate 1 of the clutch 1. The clutch 1 is closing in the period of 0.4 to 0.6 seconds. In the transition phase, we see test bench accelerates the crank train to common operating speed, and in steady state stick-slip effect in clutch 1 can be seen. So there will be another use case that will be shown my colleague Swapnil when he is doing the demonstration in a few minutes. The next is a number of enhancements in silent chain and involute sprocket improvements. The involute sprocket can now support a more detailed description of the profile at the tip and the root of the teeth. We are able to model the detailed geometry with 3 arc regions at the top and at the root. So you can see a sketch of this definition and the parameters here on the slide. So the Imola Sprocket has optional detailed request data on the contact of the tooth flanks, both on the left and the right side. We can plot different sprocket and different tooth number contact forces both on the left and the right side of the flanks. This is just an example plot of the contact forces that you can see on this plot. Next is the contact between chain link and sprocket can be set to Adams generic contact as well as two-dimensional Hertzian analytical contact, and also a modified Hertzian two-dimensional contact which is called Harris. The Hertzian 2D contact works with the material properties like Young's modulus, the Poisson ratios of the sprocket and the chain link materials. So details on the contact like penetration depth and local contact forces are divided in 4 zones per chain link that you can see here in this red representation of the chain link. User can also input the settings in the stacking order, the plate thickness per chain link. So different plate thicknesses can be defined for different plates. This is just an animation to show the the forces, which are the arrows on the animation between sprocket and the chain links. And you can see also the amplitude of the forces and the Hertzian contact pressure on the plot on the right-hand side of the slide. So in summary, we released this version last month, and the functional changes included, but not limited to, multi-thread computing, clutch element, and chain drive enhancements. Now I am handing over the words to my colleague Swapnil, who will demonstrate these new features to you.
Okay, thank you, Mustafa. So today I want to do a small demonstration for the clutch, the new enhancements, the clutch model, as well as the enhancement in the chain. I have a new virtual dynamics session over here. First, I'll start with the clutch. So I want a crank train, a gear train to bind with a clutch together. So I'll just go to the shared database and open one of the crank trains. Let's take the V6 example for this demonstration. So as you can see, it is a very standard crank train. It's a V6 engine with everything is rigid over here. So now that I have my crank train, what I want is a gear train. So I'll open a new session and I'll use the gear train wizard functionality. Of course, for this demonstration, I had prepared a property file for my gear train. It's a very simple gear train prepared very fast. It has 3 shafts. Each shaft has, of course, its own gears and bearings. So shaft 1 and shaft 2, they have 1 gear each, and shaft 3 has 2 gears. And of course, all the gear contacts, the gear contact pairs, and all the gear contact forces, everything has already been defined in this property file. So now that I click on build, so let's just prepare the gear train. As you can see on the screen, as it's not a very large gear train, it should go very fast. And there we have it, our gears, our shafts, and all the contacts have been already created. The gear ratio between both the gears, every gear pair is 2 in this case. Good. Now that I have my gear train, I want to bring it to the same template or the same subsystem where I had my crank train. So I will just import my gear train, which I just created over here. It's not a very large gear train, so it should happen pretty fast. As you see, my gear train is already here. Yeah, because in my property file, I already took care of the position and the orientation of the gear train, so it's already there. But they are not connected. I don't need my flywheel. So I will just use a dummy property file. I do not want to delete it. It's difficult. And now I can finally move on to creating my clutch. Okay, so let's give in a name, clutch underscore webinar. Yeah, I will select a property file. You can also have some property files from the shared database as examples. I have my property file. And in the clutch, so what do we have? First of all, I can select between the single clutch or the dual clutch. Yeah. If I take the single clutch, I also have I have to give in the clutch cover and clutch plate. If I select dual clutch, then I also have to give in the properties of the second clutch plate and the clutch cover. Let's first stick to the single clutch for this example. In the attachment, I can attach it on the input as well as the output side. Yeah, depending on my use case. So in this case, I need the input and the output side of the clutch. Of course, I also have this clutch spring damper option. And if I can attach my clutch with the help of parts or markers, I know my markers, so it's easier for me. On the input side, I will attach it with the flywheel, which is in a way anyways attached to my crankshaft. And on the output side, of course, I will be attaching it with one of the shafts in the gear train, which I had just created. Okay, so I have my clutch ready over here. Oh, no, of course, I forgot something. So I have to give in the normal force. So this is the technique of how you want to close or open the clutch. It can be, the force can be a function of time, it can be a function of angle, or a constant value as you desire. I'm just giving a constant value just for the demonstration, and there we have it. Now we have our clutch, which means that the crank train and gear train are now completely coupled together, and I have my entire system ready. What I'll do is I'll shift to a model with a little higher fidelity. I had created a model with dual clutch, as you see on the screen, and I'll use the functionality of multi-thread capability. So over here in the solver settings, I'm increasing my thread count to 4 to run my simulation. And now I can just start my crank train analysis. So let's give it a name for my analysis. Visiting webinar, 25 cycles, 2000 RPM, and we can just begin our calculation. So as Mustafa already mentioned, with 4 threads, you can expect an improvement in the calculation time by a factor of 2 to 2.5. With higher threads, it can go up to 3.5 or 4, or even higher if you are using HPC clusters. So this 2000 RPM, 25 cycles is a calculation of 1.5 seconds. So it should not take very long. And once the calculation is done, I will move to the post processor where I have already preloaded the results from my previous run, yeah, for the same calculation. Good, so the simulation is completed successfully, and I can move to the post processor. So on the left, of course, we have the animation, and on the right, what do we have? We have the 4 curves. So clutch red and the blue curve are the normal forces which are acting on the clutch plate 1 and 2. So the clutch plate 1 closes and opens, whereas the clutch plate 2 closes. The green and this dark blue, the almost black curve, they are the angular velocities of the clutch. So what we are able to see is the lag in the angular velocity when the clutch plate closes. Let's just start the animation. And right now what we see is that the clutch plate and the gear train are not rotating, even though the crank train has started. Now slowly the clutch plate 1 starts closing, as we see over here, and the gear train starts rotating along with it, of course. And what we are also able to see is slightly deformation on the clutch disc is leading to the slight vibrations in the angular velocity. The clutch plate 2 is of course not coupled right now. It's rotating only because of the connection with the gear train. And now the clutch plate 1 is opening and the clutch plate 2 is closing with a small overlap, which means effectively we are shifting from gear 1 to gear 2. The gear ratio in this case is 4 because each gear pair had a gear ratio of 2, which is a little extreme, but just for a demonstration. And that is why maybe on this green curve of the angular velocity of clutch plate 1, we are able to see such a large lag that even though the clutch plate was closed, the angular velocity had still not reached its steady state. Of course, you have a lot of other results. You can see the relative angular velocity, the friction coefficients, the torques. You can also see the friction power loss in the system, the deflection on the clutch plate surface. And of course, we should not forget that all the results of the crank train are still available to us. All the results of the gear train are also, of course, still available to us. You can even do your gear sensitivity analysis. And that's all about the clutch. I will now shift to a different virtual dynamics session and we can talk a little more about the chain enhancements. So again, I'm opening an assembly from the shared database. I will use the silent chain assembly. It's a simple assembly with 2 sprockets and it should open pretty fast. And there we have it, a small assembly with 2 sprockets. And of course, the first thing which you would want to do is wrap your chain. So I will take a silent chain and wrap it around my sprockets. I'll give in my settings and use 2D links for better analysis. So it selected virtual dynamics automatically selected the number of links and the pretension in the chain. First thing which I always do is I will change the graphics. So even though it does not really affect the results, just for visual representation, I find it nicer. So I went to the modifying box and changed the graphics to all instead of links, rigid links. And we can see that it's much more realistic. My chain is made of the pin plates and the bushing plates. They are all already located correctly in the sprocket. The contact is already there. And now let's have a look at some of the parameters of the chain, the new parameters especially. Okay, where is my dialog box? Here it is, just a second. Sorry for that. So this is my dialog box for the silent chain. One of the nice features which we have is this stacking property. So you can define the pin plate and the bushing plates in much more detail as you desire. So you can define different sections. So here I'm taking 2, 0, 1, 0, 2. So I'm defining 5 sections in the pin plates where 2 are 0. And in the bushing plate, I'll do the exact opposite. So I'm taking 0, 1.5, 0, 1.5, and 0. So I have 5 sections. The total width, of course, of all the sections together should be equal to the chain width. And let us apply our new modifications. One of the other nice features which we have is the link exporting the geometry. So the sections which we just created, the pin plate and the bushing plate which we just created, we can export it very easily. There are in a Parasolid or many other CAD formats, and it will export one geometry for the pin and one for the bushing plate. So the export is done. It should have gone to my working directory, yes. And now we can actually just shift to external geometry and set up our pin and the bushing links. So first, as you see, there are 2 geometries which have been exported over here, the chain bush and the chain pin. First, I'm setting up the pin, so I will import the pin geometry. It will create a local copy, that's okay. And that's it, it's done. And we will also do the same steps for the bushing. Oops, wrong folder, sorry. Browse, yeah. And I go to the chain bush, and we have our external geometry all prepared. So let's just accept the modifications. The internal geometry, of course, will be deleted, and the external geometries for every link will be imported and positioned correctly. Okay, I think the process is almost done. And yes, I can close this. And we have our chain with the external geometry. If you remember, we created a chain with 5 sections, 3 in the pin and 2 in the bushing links. And that's what we can see over here. It was done in a matter of minutes. And you can, of course, change the settings, you can change the thickness and come back. Of course, as usual in Virtual Dynamics, you can just go to dialog boxes and press F1. You will get a lot of information of the different parameters, how it has been defined, how to define these segments. You can define all of those things. Of course, if you go to details, then the numbering, for example, how the chain links are numbered. This is really nice that now every pin is divided into 4 zones. So you can actually investigate the 4 contact zones individually. And you can also read a lot more in the help. Now we have looked at the links chain. Let's have a look at the sprockets, the involute sprockets. So this is the dialog box. Of course, many of the things will be standard as earlier. You have the left and the right teeth with the root and the tip, so the bottom and the top, and you have this advanced profile. So now you can define the root and the tip in much more detail with this 3 arc or 3 radii method. Again, I pressed F1 and I go to my help. So a lot of things, how everything has been done is defined over here properly. It's a very smart algorithm according to me. What you have to do is just, you have the involute and the root radius, the base of your sprocket. All you have to do is give in the 3 radii of your transition, and the center points of this upper arc and the lower arc will be calculated automatically by the software such that the transition from your involute to the root radius are seamless. So that's about the geometry modifications. You can do it everywhere. And if you look at the context, so of course you have the Harris, Hertz and user. Right now for external geometry, I would use the user method where I will give the stiffness and exponent. I have the analytical Hertz method where the Poisson's ratio and the Young's modulus are important for a faster calculation. Of course, you can export the Sprocket also for an external geometry very easily. I'm shifting back to internal geometry, and now I have this new functionality, chain link request. So I wrote 1, 2, and 3. What I'm doing is I'm asking for the software to write out the detailed analysis results for these 3 links, 1, 2, and 3, which you will soon see in the post processor. I will use my, of course, soon to be favorite feature. I'll increase the thread count to 4 in the solver settings for a faster simulation. It's a very simple chain system. Let's give it a name. So, silent chain webinar. 5,000 steps for 30 milliseconds should be good. And we can start the calculation. Again, for such a simple model, even in such a simple model which calculates in under a minute, you can expect a time improvement by a factor of 2 or 2.5. And my simulation should go through pretty fast. Of course, as like in the previous case, I already preloaded the results from my previous run for the demonstration. So I'll just shift to the post processor. Let's just immediately start the animation. Yes. What do we have? We have Sprocket 1 and Sprocket 2, our chain. This red link which we are seeing over here is the link number 1 for your orientation. You can see the force graphics. And in the results, you can see a lot of different results. So if you remember, link 1, 2, and 3 is what I had requested. I can see the detailed information like the normal force, for example, as we plotted over here for link 1, 2, and 3 for each zone individually, and also in contact with Sprocket 1 and 2. And you can also look at many different results like normal force, tangential force, the penetration depth, the Hertzian stress, also the tooth number where the sprocket is coming in contact, which tooth is coming in contact with the chain. The global results like earlier are still like the joint force and the torques, all of those results are also still available. I think that was all about the demonstration that I wanted to show today. I hope it gave you a good overview of our new features and you enjoy using them. Thank you.
Thank you, Swapnil. So I would like to once again remind you that you can ask your questions by typing them on the panel that you have on your screens. So I will start going through the questions and try to answer them. So the first question is, what's the absolute calculation time for the inline 6 diesel engine? So if it is meant by the EHD model that has 7 main bearings modeled as elastohydrodynamic, it's a very high fidelity model. If you run it again on a laptop with a single core, it took about 11 hours. If we run the same model with 8 threads, it took only 3 hours. So it is in the order of hours, but it is very high fidelity, complicated model. So the second question is, will every thread used in a simulation need an own license? In other words, will 8 threads use 8 times the licenses? No, actually it's not the case. So if you are running, say, a crank train model, of course the user needs a crank train license. And if you want to run it on multiple threads, you only need 1 seat of multi-thread computational module. So which means per user or per model, if it is crank train or if it is valve train, you need 1 seat of crank train or valve train license, as well as a multi-threading capability license. So if you're interested in trying this, please just contact me or Swapnil, that you can find our contact details. Just a second, I'll pop it up. So here are our contact details. If you're interested in trying this multi-thread computational capability, please just let us know. The next question is the clutch element included in the basic virtual dynamics package? Yes, indeed, it is included. So every licensed user can access to clutch element. So the next question is, how is the clutch modeled? Is it just a simple step function defining the closing of the clutch?
Okay, I'll take this one. No, the clutch is not a simple function or a simple step function. It's actually a properly defined friction model. And I think Mustafa also mentioned it's available in the presentation that this friction effect is modeled through this Lou-Gray, the Lund and Grenoble friction model. It is first order non-linear differential equations are used over there. The functions which I maybe used in the demonstration today, they were just there to simulate the opening and the closing of the clutch. So the method of how the clutch will close. In my case, for example, I had a linear closing of the clutch in 0.2 seconds, but you can define any different function you need. But the clutch does not use a specific function, and that's why in the demonstration we were also able to see the vibrations, you were able to see the lag, that even though the clutch plate had closed, there was still the coupled velocity of the gear train had not reached immediately. Yeah, I think this should answer the question.
Yeah, thanks, Swapnil. The next question is, if it is a friction model, can I really use the model to minimize the slipping?
Yeah, it is actually, this is just in continuation with the previous answer in that case. So that is our aim. Yeah, the clutch model, it considers the relative velocities, inertias, the static as well as the Coulomb friction, the Strybeck effects to model the clutch behavior. So you can, of course, use it. You can, if you go to the post processor, for example, the relative angular velocities, the friction power losses, all of these things are already standard outputs. And that would be the things which you would want to normally optimize if you're looking at the clutch element. So all of them are modeled in realistically with physical models, and this model, this clutch element can be used to optimize these effects, the closing and the opening of the clutch, the start effects, all of those things. Yes.
Okay, thank you, Swapnil. The next question is related to chains. What if I don't have the detailed profile of the sprocket? Is it necessary to have them?
The sprockets, no. So yes and no. Of course, the standard method where you can define the entire sprocket, the tooth and the tip radii with just a single radius, single arc, it's still available. The profile detail, the advanced profile, which I showed today in the demonstration, it is an additional functionality. This profile, for example, becomes very important if you want to investigate the root stress in your sprocket, for example. And the general opinion from the experts in the industry with whom we could talk to, it was that this 3 arc, the 3 radii definition would be the state of the art. So if you want to do a detailed analysis, you have this option available, but you can also, if it's not important for you, just use a simpler geometry and not spend much more time in modeling. Yeah.
Okay. Thank you for the answer, Swapnil. I'm moving to the next question. It is, are all virtual dynamics elements thread safe using Adam's terminology? Except piston ring dynamics, yes, all the elements are thread safe. So this multi-thread computational capability works for all elements except piston ring dynamics at the moment. So let me see the other questions. will also models with regular hydrodynamic bearings 2D, 3D rigid benefit from multithreading? Yes, they can benefit from the multithreading. Let me see if there are other questions. Yeah, there is one. Has flex to flex been added to the available contact types is the question.
So I'm guessing this question is for the chains. In a way, yes. So you can still use flexible bodies in the chain. You can mesh the links and just import them, but it's not really been incorporated in the system. So if you see the contact, you can only define the stiffness and the stiffness exponent. So you can still have the dynamics of the chain if you want, but it was not really included in the contact type, if that is exactly the question what you wanted to ask.
So the next question is, will the external geometry chain work with the internal geometry sprockets?
It will work, but I would not want to do that. Yeah, so because there is this Hertzian analytical stress also available, if you have an external geometry and you use internal geometry on the sprocket side, then the software will not crash. What it will do is it will recalculate the necessary values for the contact, even if you are using the user setting, and it will use the Hertzian analysis in the background. So that's why actually I did not want to spend too much time in the demonstration. So I showed you how to create the external geometry in the chain. But for running the simulation, I still had an internal sprocket. So I shifted back to the internal geometry before I started my simulation.
Okay, so thanks for the questions. We are reaching closer to the end of the time that is reserved for this webinar. So for now, I would like to ask you a couple of poll questions. If you can respond, I would really appreciate. So the first poll question you will see on your screen. Have you started using Virtual Dynamics 2019.0? So if you can provide feedback to this, I would really appreciate. So I just give you a couple of more seconds, and then I will move to another poll question. So there is actually just one another. Yeah, thank you for the feedback. Now I will just ask another poll question. And this is the last one. Do you receive release announcement emails? If you can respond to this, I will also appreciate that. And if you don't receive these, and if you want to receive, please just contact us. So that we can subscribe you, that we will make sure that you will receive this release announcement emails. Okay, thank you for the feedback. I have just closed this poll question. I would like to remind you that there are 3 handouts available that you can see them on your screen. So Virtual Dynamics general brochure, this what is new document that I presented to you, it's in PDF form. You can download it from the handouts section. And also the e-motor generator module brochure is also available among the handouts that are available for you to download. So thank you very much for your time and for your interest. We appreciate your interest, and if you have any further questions, please just contact either myself or Swapnil.
Thank you.